Okay, let's get started. Uh, in the last class, during the last class, I brought up uh, the question of was could we find a way of not measuring every state variable, which is, by the way, the requirement if you want to do full state feedback control. If you want to do full state feedback control, which means it means you need to feed back every member of X vector, and feeding back every member of X vector, when you go about implementing it, means you need one sensor for each of the state variables to measure them and to feed them back. And in reality, it may not be affordable. Our budget for sensors may exceed the limitation we put, or it may not be physically possible to measure certain variables. They're out of access, the temperature is beyond our control. We can't physically reach there to put a sensor there. What then we introduced was the concept of an observer, which is an algorithm. It's a computer program that receives two inputs, only two inputs. One of them is the input that the physical system receives, U. So our observer, which sits in this box, in this gray box at the bottom, receives the input to the system, as you can see here, in addition to the output from the physical system. This is a single measurement. So if the system has this output, this is being measured, as well as the input. The rest is done in calculation. So what are we doing in an estimator or an observer? We take advantage of the information that we have in the form of the model of the system, and we predict things. What do we predict? The first thing we predict, which is necessary for our full state feedback control, is the state vector, x. And to distinguish it from otherwise measured x, we put a little hat on it. So we call it x hat for the estimated x. This is what our model predicts x would be at each time. So it's a continuous prediction by the time. So as time goes on, the physical system is running and our algorithm is running in parallel. So it continuously receives sampled input, continuously receives sample from y, and it continuously generates x hat, which is then used as part of our full state feedback control, which requires multiplying that by the controller gain k as a vector, which then goes into controlling the system. Now, I mentioned no model is perfect. No model is perfect, and there are multiple possibilities where the prediction of the model would be different, or reasons for the prediction of the model to be different than the actual physical system. And it could be as simple as our model not knowing the initial condition. If you don't have the initial condition, or you use the wrong initial conditions, your model would predict something different than what actually happens. And on top, your measurements. So if it is a mass spring damper system, if your mass is off by a few grams, or stiffness is off, or your damping coefficient is off by a few units, your prediction would be different. And let's just put all of those possibilities aside and say, let's assume we have perfect information. So we know all the initial conditions. We have measured this to perfection, all the parameters. But what could happen over time is that the system could change over time. Imagine that you still have, for simplicity, the mass spring damper system, and over time the value of mass changes. You have no way of knowing the value of mass is changed because you don't measure that. You don't continuously monitor the system to see if the parameters is changing. The only things that you monitor continuously is the input to the system and output from the system. So all of these are reasons for correcting our prediction, not simply relying on the fact that we have a model and forget about the rest of possibilities. So that's why we have a built-in correction as part of our estimator algorithm. What is that built-in correction? We will continuously monitor the output of the system, the physical system that is, and compare it to what the model predicts as the output of the system. So this is y hat, the prediction of the model for the output. We continuously compare it to the actual output of the system, And the difference would be error in prediction. So that's an indication of how off our model, how off our estimator is. And then we'll take it and multiply it by a series of gains. This is the same dimension as the order of the system. So if this is a second order system, there are two L values here. And this makes a correction. This goes as an input to our estimator. So if y hat is less than y, so if we're under predicting, our estimator under predicts, this puts an additional input to the system, so it will push the output up. If the estimator is over predicting, it will reduce the actual input to the system, so it will bring y down. And in the process, the reason we are doing that is because we need x hat. The whole purpose of this algorithm is to get x hat done. That's the whole ultimate purpose. So in the process, x hat also gets corrected, and we have overall a better control system. I mentioned about the process of designing an estimator or an observer, and the process is to recognize that A minus LC is the A matrix of the estimator. So A minus LC, this matrix, is the A matrix of the estimator. This matrix, which is the same dimension as matrix A. So this is the main matrix, and the exact same methodology that we used for designing a full state feedback controller is applied here. So we put the eigenvalues of the A matrix of the observer somewhere that delivers acceptable results. So then the next thing we did, we looked at a couple of examples, and the last example that we stopped on was this example. So we said, let's look at this cascade of tanks as our system. Let's establish, first of all, is this system observable? And we looked at two possibilities. One was if the output of the system, so if y value was h1, that was possibility number one. And possibility number two was if y was h2. And we established that if y was h1, the system was not observable. If y was h1, the system was not observable. And if y was h2, the system was observable. Which meant, and the reason was that if your output is h1, h1 is not being affected by h2. Take a look at this system. h1 is not being affected by h2. And that's why if you limit the output to h1, you don't have that built-in information in h1, so you can't extract h2 rather from it. So you can't extract h2 from an observer that simply looks at h1 as the output of the system. And it seems logical. But on the other hand, if your output is h2, h2 is being continuously affected by h1. So that information is built into h2. That's why you can estimate h1 simply by measuring h2. So the next step is to design an observer. So why don't you go ahead and design an observer for the case that is observable, for the system that is observable. I'll give you a minute. To do that, and we have a specific goal. So we have specific numbers. So we have C1, C2, A1, and A2. So we are going to work with these numerical values. And we want the observer to be 5 times faster than the physical system. And I mentioned the logic. Let me repeat. Why do we want the estimator to be faster? So generally, we want the estimator, the logic that is predicting the state vector, to be faster. So our prediction is more reliable this way, because we don't run the risk of our prediction being delayed, falling behind the actual physical system, so we have more faith in the estimation. That's why we generally want the estimator to be faster than the actual system. So we established that this system was observable. So if the output of the system is H2, which we are signaling by choosing C vector as 0, 1, this is an observable system. So we want then to go ahead and design an observer that is 5 times faster than the actual system. But before doing that, we need to establish the speed of the actual system first. So we need to know how fast the open loop system is, so we can design an observer that is 5 times faster than the open loop system. So how do you establish the speed of the open loop system? What do you need to find in order to establish the speed of the open loop system without any observer? You need to look at the eigenvalues of matrix A. So with these numbers, let's go ahead and get numerical values for A. So we have A is minus, it's 10 over 12, so minus 5 6 here, 0. Then we have 10 over 24 positive, so 5 12 here. And then minus 5 over 24, so minus 5 over 24. This is A. And B with these numerical values is 1 over 12 and 0. And C remains the same. So what we will do first is we'll go ahead and find the eigenvalues of matrix A. And for that, we need to find this determinant and set it equal to 0. So this determinant is lambda plus 5/6, 0 minus 5/12, lambda plus 5 over 20. So this is the determinant, which gives you lambda squared plus yes.
So why are you not finding A observed matrix in this case?
We will. So the question that I received is, why don't you start by looking at the A of observer first? And the answer I gave is, look at the requirement. We want to design an observer that is 5 times faster than the physical system. So we need to first of all find out how fast the physical system is. That gives us a target to become 5 times faster. Very good question. Thank you. Okay. Could you please double check that? Is this correct? I get the same thing. Okay. So we need to find the two roots of this. So what are lambda 1 and 2? So we need to find lambda 1 and 2. Could someone please calculate this and give us the numbers? Is this right? Minus 0.44, is that what you got as one of the two lambdas? Yes, it should be divided by 2. So one of them is minus 0.22 and the other one is minus 0.8 roughly. So the two numbers are these. Okay, so here's an important question with the exam coming up. Which one of these two poles would define the speed of this system? We know the location of the poles define the speed of the system, but we have two. Which one? In other words, which one is the dominant pole? Which one will define the speed of the transient response? The one that is closer to the origin. So this is the dominant pole or eigenvalue. These are the same for the system. So when we are designing the observer, we want the observer to be 5 times faster than this one. So where do we want the eigenvalues of the observer then? So for the observer to be 5 times faster, it means lambda 1 and 2 should be 5 times the dominant pole, minus 0.22. Just to make it round, we'll just put it at negative 1. So we want to put the two eigenvalues of the observer at negative 1, so the observer is 5 times faster than the physical system. So A of observer is equal to A minus L times C. So we have the A matrix here. As I mentioned before, let me repeat, A is a vector. A is a vector, and A, in order for the dimension of L times C to become the same as dimension of A, which is 2 by 2, L has to be 2 by 1. So we have L1, L2, which then gets multiplied by our C, which is 1 by 2. Our C is 0, 1. This is the configuration that gives us an observable system when the output is H2. So let's go ahead and find this matrix. So this L1 times 0 is 0. L1 times 1 is L1. Same pattern here. So if we subtract this matrix from A, we'll have as the A of observer, here we have minus 5, 6 because 0 is subtracted. Then we have 0 minus L1, so we have minus L1. Then we have 5, 12 subtracted by 0. And then lastly, we have minus 5 over 24 minus L2. This is the A matrix of the observer. Now we want to choose L1 and L2 such that the two eigenvalues of this matrix are both going to be equal to negative 1. So we are looking for two numbers for L1 and for L2 so that the eigenvalues of this matrix are both located at negative 1. So how are we going to do it? The next step is to find those eigenvalues. So determinant again of lambda I is A of the observer is equal to lambda plus 5, 6, L1 minus 5, 12, lambda plus 5 over 24 plus L2. This is the determinant that we need to find. So the first term is lambda squared plus 25 over 24 plus 5, 6 times L2, all divided, multiplied by lambda. Plus 25 over 144 plus 5, 6 times L2 plus 5, 12 over L1. And this is the characteristic equation of the observer. And what we want is the two eigenvalues to be equal to 1, which means the characteristic equation should be lambda minus 1 times lambda minus 1, which will give you lambda squared minus 2 lambda plus 1 equals 0. So that should be the characteristic equation if we want the two eigenvalues to be located at negative 1. And I made a mistake, so catch my mistake, please. It should be plus 1. If you want the lambda, the eigenvalue to be at negative 1, the expression should be lambda plus 1 times lambda plus 1. So this should be plus 1. This should be also plus 1. So this becomes plus 2 lambda. So the coefficient of lambda squared matches, so that's good news. Then our goal is to match the rest of the coefficients. So the first expression we get is 25 over 24 plus 5 L2 over 6 is equal to 2. That gives you 25 plus 20 times L2 is equal to 48. So L2 is 23 over 20. So that's L2. And the next expression is to find L1. So we have 25 over 144 plus 5 over 6 times 23 over 20. I'm substituting for L2 plus 5 over 12 L1. That is equal to 1 by comparison, by comparing the coefficient of this desired equation with the actual equation that we got. So you can calculate L1, whatever that number is. So L1 will give you another number. And the bottom line is, with these two numbers, you have an observer. With these two gains, rather, you have an observer that receives the input of the physical system and output of the physical system. What are those? Input of the physical system is, let me go to the figure where we have the drawing. Input of the physical system is U, the flow to the first tank. Output of the physical system is the level of the second tank. So it measures these two, and it estimates both H1 and H2 based on these measurements. And the estimator is 5 times faster than the physical system. What does it mean for it to be 5 times faster? It means the estimator reaches a steady state 5 times faster, 5 times sooner than the physical system, because each of these two, if you give a constant input to the first tank, each of H1 and H2 will settle as at a steady state value, and it takes a while for it to reach there, based on the time constant of each of these two tanks. But the virtual tank that we made in our computer as the observer would reach a steady state 5 times faster. So we made a tank that is quite faster than the actual tank. And the other fact is we have a correction built into it. And these L1 and L2 are the correction games. Please remember that. So these two will continuously correct the estimate of the tank, so of the virtual tank, to make sure we can control the system, because we need the state vector to do that. So I know we have done quite a few full state feedback controller, but let's do another practice. Design a full state feedback controller to place the closed loop poles to make the system 2 times faster in response. So we want the closed loop system to be twice as fast as the open loop system. So I'll give you a minute to design the controller, and then we'll work together on it. So again, you look at the dominant eigenvalues of the open loop system, and we are designing the closed loop system to be uh, twice as fast. We don't have any other requirements other than making the closed loop system twice as fast. Again, the question is, which one of the two open loop eigenvalues is the dominant one? We agreed that the one that at minus 0.2 was the dominant one. So for the closed loop system, So for the closed loop system, so for full state feedback, we'll choose the two lambdas to be located at 2 times negative 0.22 something. We'll just use them to be equal to negative 0.5. Anything to the left of that would be at least twice as fast. So if you put it at negative 2, it would be at least twice as fast. So that means the characteristic equation for that is going to be lambda plus 0.5 times lambda plus 0.5. So that's the characteristic equation, which is lambda squared plus lambda plus 0.25 equals 0. So that's the characteristic equation of the closed loop system. Now, what is the A matrix of the closed loop system with a full state feedback? It is A. So A of closed loop is A minus B times K. For full state feedback control is A minus B times K. So we know what A is, so let's calculate B times K. So B times K is going to be equal to, what was the numerical value for A? For B rather. So what's 112 and 0? So it's 112 and 0. This is 2 by 1 multiplied by K1, K2. So the result would be 2 by 2. So this is going to be K1 over 12, K2 over 12, zero, 0. So this is B times K. We need to subtract this from the A matrix to get to a closed loop. It's going to be equal to. So the actual A matrix is minus 5 over 6, 0. So minus 5, 6 minus K1 over 12. This is minus K2 over 12 because the second element is 0. The second row is minus is 512 and minus 5 over 24. So that's A of closed loop. Then the next step is to find the eigenvalues. So let's go ahead and find the eigenvalues, which requires finding lambda I minus A closed loop. So it would be lambda plus 5 sixths plus K1 over 12. And this is K2 over K2 over 12. Here we have minus 5 over 12 and 5 over 20. Oh, I forgot the lambda plus. So lambda plus. So lambda plus. So I'll let you finish this. So again, We have the characteristic equation that is desired as equation 1. You will find another equation from here. You call it equation 2. And by comparing the coefficients of equation 1 and 2, you'll find K1 and K2. So you will find the two controller gains that would put the eigenvalues at negative 0.5, which results in a system, in a closed loop system that is now twice as fast as the open loop system. So you have an observer that is 5 times faster, and you now, with the help of that observer, without that observer we can't do full state feedback control, because that observer gives us the x vector, the estimates the state vector, which is essential for calculating um, the input to the closed loop system, to the uh, and creating the full state feedback control. Yes.
You got the eigenvalues to be negative 0.5. Did you just take the negative 0.44 and round that up?
Negative 0.22.
We have to multiply it by 2 to make it twice as
Sure.
fast.
Yes. Yeah, I just rounded up. So it was, so negative 0.44 gives you exactly twice as fast. Negative 0.5 gives you a little bit more speed, which is desirable. So to make it easier to calculate, I use the round number. Any other questions? Okay, so what I'm going to do next is to spend time on the sample exam that I posted on Blackboard. So the model I want to follow is to give you a minute or two to attempt at solving, and then I'll show you the solution here. And in the exam, you will not have your notes, but here you have your notes. This is not a practice exam, so please take advantage of your notes. So what we are, just to help you here a little bit to get to the answer a little bit easier, you can assume the current that passes through this branch is I1, and the current that passes through the second loop is I2. So if what passes through here is I1, and what passes through here is I2, what passes through this portion is I1 plus I2. Just a heads up. So we have two loops here, and we can write Kirchhoff's voltage law for both loops. So for the first loop, we have V as the source of voltage minus R1 times I1 plus I2 minus L1 d over dt of I1 plus I2. This is in a capacitor, so that becomes minus 1 over C1 integral of I1 dt and minus R2 I1, that is equal to 0. That's our first loop. The second loop would give us minus, so that the voltage drop across C2 would be minus 1 over C2 integral of I2 dt minus L2 di2 over dt, and then plus I1 R2 plus 1 over C1 integral of I1 dt equals 0. Now these are the two mixed integral differentiation equations. If we didn't have the qualifier inside the parentheses that says no integrals, then that would have been it. Because it says please get rid of any integrals in the differential equation, we take advantage of the following. So we take advantage of the fact that Q1 is integral of I1 dt and Q2 is integral of I2 dt. So the charge is integral of current. That's the definition of charge. So you're going to write everything in terms of charge and its time differential instead of mixed of integral current and its integral and its differential. So the first equation therefore becomes, so I becomes Q dot. So the first equation becomes V minus R1 Q1 dot plus Q2 dot minus L1 times Q1 double dot plus Q2 double dot minus 1 over C1 Q1 minus R2 Q1 dot equals 0. So that's what the first equation becomes. Similarly, the second equation becomes minus 1 over C2 Q2 minus L2 Q2 double dot minus plus rather R2 Q1 dot plus 1 over C1 Q1 equals 0. So now we have two second order differential equations. So these two are together are the model of the system. So that's the differential equation model of the system. Now, knowing that we have two second order differential equations representing the system, what is the order of this system? It has to be a fourth order. The highest time derivative defines, so we have a second order, another second order. So it's a fourth order system, which means when it comes to finding the state space model, one of the first steps to take is to define the state vector. So what is the state vector for this? What is x? X, anybody?
Q1, Q1 dot, Q2, Q2 dot.
Absolutely, you got it. So it's going to be Q1, Q1 dot, Q2, and Q2 dot. These are the four state variables, and there is no right or wrong order for these. So it could also be Q1, Q2, Q dot 1, Q2. It could be Q dot 2, Q1, Q dot 1, Q2. There is no set order. It just needs to be one order, and you need to stick with that order. Okay, so the next step is simply find. So from this equation, this is easier to see. So from this equation, we'll find Q2 double dot, which is necessary for finding derivative of Q2 dot, the fourth member of the state vector. From this equation, we'll find Q1 double dot, which is the derivative of the second member of X. And we'll write the A and B and C and D matrix. So the input to the system is our voltage, and the output could be anything that you define because it's not defined here. So you can define the output to be, for example, Q1. Or any of these four, or any combination of these four could be your output. So please work out the rest of the steps. It should be straightforward. The A matrix. So please go ahead and if you have some time at the end of the class, I'll come back to this. So let's keep this here. So the third problem is a pendulum of length L rather, with a tip mass of m. We want the differential equation describing the motion. And again, I'm going to give you a minute to set this up, and then I'll show you the solution. And if you're done with the first portion, number 3, please continue to number 4 and number 5 and number 6. These are all connected questions. So if you're done with number 3, please continue. So the base equation is Newton's second law in the rotational form. Second moment of inertia about point O times angular acceleration of the mass, which is theta double dot, is equal to sum of all the moments about the same point. So what moments are there? So you have the externally applied moment. This is what causes the link to move. Then you have the friction that is modeled as a viscous friction. So it's proportional to angular velocity, so minus b theta dot. And the reason it receives a negative sign is because it opposes motion. So if this is theta positive, it is going to be in negative direction. And the other moment about point O, which is also in negative direction, is the moment caused by force mg, by the weight. So mg times the moment arm. The moment arm is this distance, perpendicular to the vertical direction. So it's L times sine theta. So minus mg, which is the force, times L sine theta, which is the moment arm, would give you that moment created by the weight. So this is it. This is the differential equation. You can always rewrite. So you have 1/2 ml squared theta double dot plus b theta dot plus mg L sine theta equals to the input torque. So that's your differential equation. That's the model. And from this equation, you can find the equilibrium position or positions of the system. If you set all the dot terms equal to 0, as well as the input, so if you put everything that has dot and the input both equal to 0, you'll arrive at mg sine theta equilibrium has to be equal to 0. So what you will get to is at equilibrium, you have mgl sine theta equilibrium 0, and that gives you two possible positions. So theta equilibrium can either be 0, or as the second possibility, it can be angle 90 degrees, which is pi radians. So there are two angles, 0 degrees and 90 degrees. 180 degrees, I apologize. So 0 degrees and pi, which is 180 degrees, these both are the equilibrium positions. And the next question asks you to find a linearized version of the model about each of these two equilibrium positions. So what you need to realize is, according to Taylor's series expansion, sine theta, when theta is approximately equal to 0, or it's close to 0, is equal to theta when theta is expressed in radians. Please remember that. So theta must be in radians. And the same thing when sine theta, the same term that is causing nonlinearity, when theta is approximately equal to pi, with a bit of manipulation, you can show it's equal to minus theta. With a bit of manipulation, you can show that sine theta can be approximated as minus theta. In reality, it's pi minus theta. That's the equation. But you can just assume that the new theta is pi minus theta and rewrite it as minus theta. Okay, so with this approximation, then the differential equation simply becomes 1/2 ml squared theta double dot plus b theta dot plus mgl theta equals t. And with the other about the other equilibrium, the differential equation becomes 1/2 ml squared theta double dot plus b theta dot minus mgl theta equals t. So two different differential equations. One about the stable equilibrium and the other one about the unstable equilibrium. So about stable equilibrium, and this is about the unstable equilibrium. And the next step is asking you to find the poles and eigenvalues of each of these two linearized. So you can go through the route of poles, which means you have to find the transfer function, or you can go through the eigenvalues route, which means you need to have to find matrix A. Either of the two would give you the exact same answer. So let's go through the route of transfer function. So what you need to do is you need to take each of these two differential equations into Laplace domain. So one possibility. So the transfer function would be theta over t when they're both in Laplace domain. That's the transfer function that we're talking about. So for one you get 1 over 1/2 ml squared s squared plus b times s plus mgl. That's one of the two transfer functions. This is about the stable equilibrium. About the unstable equilibrium, you get the same theta s over t of s as the input. Everything is the same except for the last term that becomes negative. That's the only difference when you take both of these into Laplace domain. And now you're ready to calculate the poles. You deploy the quadratic equation to find the two values of s that will make the denominator go to 0. So it's minus b, which happens to be b in this case, plus minus square root of b squared minus 4 times, so it's 2m squared g l cubed over 2a, so it's over m l squared. And the other one is similar, so S1 and 2 for the other one is quite similar. So you get minus b plus minus b squared plus 2m squared gl cubed 2 power 1/2 over ml squared. So I'm going to give you a minute to look at these set of eigenvalues and tell me, what do you see as different between these two cases? Because that's exactly the next question. It asks you to look at these values and explain the expected behavior. In other words, where are these two poles for each of these two cases? Yes.
With the unstable, have like a J component for stable.
Yeah. So how are you thinking about it?
I guess when you add something to b squared, you subtract it from b.
Mm-hmm.
On the other one,
Mhm.
you know it's gonna be a negative.
Can you rephrase by saying, for this case, for the second case, we know under the square root. I'm sorry, under the square root is going to definitely be larger than b.
Yeah.
Because it's b squared added to its a positive number. So under the square root is b squared plus something. So what comes out of the square root is definitely larger than b. You can't say the same thing here. You know the opposite here. So what comes out of the square root for the first case is definitely less than b. As a result, what you get for this case, what you get is you get 2 for the stable case, which is in a way cheating. We know ahead of time that this is stable. We're just trying to relate them by calling stable. So in other words, when theta is close to 0, so theta close to 0. So for this case, which comes from this, we have the two eigenvalues, or the two poles, are going to definitely be two real and negative eigenvalues. Why? Because b is going to be subtracted. B is going to be subtracted by something that is less than b, so it's further negative. But the opposite is, the plus is important. So what you add to b, or to negative b, is definitely less than b, so it's not able to push it to the other side. So it's going to remain negative. So it's going to be 2 real and negative poles, which means stable behavior. And of course, the type of stable behavior, whether or not there would be oscillation, depends on relative numbers for B, M, G, and L. So the combination of M, G, L, and B could be that the system is underdamped, which means it could be that this becomes a negative number, so you have an imaginary part, so that means oscillation. But also you could have a case where the combination of B, M, G, and L gives you always a positive number under the square root. So there is no imaginary part to the poles, so there is no oscillation. So you take your pendulum, just swing it, but the value of the damping and M and G is such that it simply just returns. It doesn't go beyond 0. Going beyond 0 and coming back means oscillation. But if you have a case where you just disturb a system, but it simply slowly swings back and gets to 0 and stays there, that's a critically damped or even over damped system. So it's possible to create that conditions. So we just call it stable. We are not going to say whether or not it will oscillate. Now for the other case, which we already called unstable, but really means theta close to pi, we have 2 real still. So I should qualify that. It's not necessarily real. Let's go back to the first case. If under the square root, we already discussed that. If under the square root becomes negative, it's no longer it's going to stay real. So it becomes complex. But so let's just qualify that. So could become complex. But what is important is that the real part will stay negative. That's what is important. So for the unstable, you have 2 poles where one of the poles has positive real part. That is the most important fact. That one of the two poles will definitely have a positive real part. And that will cause the system to be unstable, which means if you have the system perfectly balanced at the equilibrium and you just tip it a little bit, it will not going to oscillate around that equilibrium. It's just going to go away, which is the definition of instability. The response will grow, will get very large. While we're waiting for you to catch up, the format of the final exam would be similar in the sense that you have a system where you have to find models, you have a system or two where you have to design a full state feedback controller, a system or two where you have to design observers. And you have always to be able to explain the expected response based on location of poles. So that means you have to be able to find location of poles and eigenvalues. So these are the type of questions that I'll be asking you, so no surprise. Okay, are you ready to move? Is there any questions about the previous parts? Yes, sir.
Is the exam going to be 1 hour again?
The exam, I believe, is going to be 90 minutes. 90 minutes. And by the way, most likely on Thursday I will be traveling, so our TA would be here, but the deal is exactly the same. What I want you to do as soon as you arrive, put everything that you don't need, including your cell phone, in your bag and put the bag in front of the class. So I don't want you to jeopardize your fair grade, so make sure nothing is in your possession except for your calculator and something to write with. That's all you need, so everything else should be in your bag.
Will we have any more assignments after the exam?
Let me finish this and I'll explain. Okay. Okay, so we're going to now look at number 7 of the sample exam that we posted. So we are dealing with a mass damper spring system that has a damping ratio of 0.7. This is open loop. No control involved yet. So the open loop system is underdamped. It has a damping ratio of 0.7. And the ratio of M and K are such that is such that the natural frequency is 1 radians per second. And also you're given the value of the mass to be 1 kilogram. Design a full state feedback controller so that the closed loop system now has a damping ratio of 1. So the closed loop system behaves as a critically damped system, and its natural frequency is double, so 2 radians per second. Also find the pre-filter gain, and as you recall, the purpose of a pre-filter gain is to make sure the steady state error goes to 0. Try designing this controller. I'll give you a minute and then I'll start the solution here. So let me explain how I got this matrix A, matrix B, and matrix C. So this, for the standard second order system, the A matrix is 0, 1 for the first row, and the second row is minus K over M, which is minus omega N squared, for row 2, column 1. For row 2, column 2 is minus 2 zeta omega N. So if you plug in those numbers, you get minus 1.4, minus 2 times 1, 0.7 times 1. So that's how we got the A matrix. The B matrix is 0 for the first row and 1 over M for the second row. So that's why you needed M. So 1 over M is here, and C is 1 and 0, assuming that the output of the system is the displacement. When we move to designing, one common mistake I want you to be aware of that is that sometimes students in the final exam mix up between output feedback and state feedback. Please avoid that mistake, because if I ask you to design an output feedback control and you design the other one, you'll get no credit, because simply you didn't know which one was what. So please be aware and look at the question very carefully, which controller you're being asked to design. So that's it. So this is A closed loop, A minus BK. So the first step that I took was to calculate B times K. B is 0, 1, K is K1, K2. So B times K becomes this matrix. Because we want to put the eigenvalues to arrive at a specific value of a natural frequency and damping ratio, we need to find the eigenvalues. And you can see that K1 and K2 will affect the value of the eigenvalue. So, the determinant becomes lambda here minus 1. Here's a potential place for making a mistake. So you find the characteristic equation from A closed loop, and you know you need to get to a certain value of zeta and omega n. And if you look at the definition of the problem, there are 2 values of zeta and 2 values of omega n. Which value of zeta and omega n are you going to use here? 1 and 2, and the reason is this is what we want to hit. We want to get to zeta of 1 and natural frequency of 2, because the other one is readily available. If you plug the other one in, and you make no math mistake, you'll get K1 and K2 both equal to 0, because you're not trying to displace the eigenvalues at all. So please be aware of that. So if you set those in, you get 2 equations. You see that 1.4 plus K2 has to be equal to 2 times 2, 4. And the other one is 1 plus K1 has to be also equal to 4. So this way you can find K1 and K2, which will put the eigenvalues where you would effectively have natural frequency of 2 and damping ratio of 1, which is a critically damped system. basically repeated eigenvalues at -2. And calculating KR is fairly straightforward. There's a formula for it. You just need to be able to find inverse of A closed loop, which is A minus BK. You need to find the inverse and then pre-multiply it by, this is 2 by 2, so you need to pre-multiply it by B and post-multiply it by C, so you get a number, and then get -1 divided by that number. There is a formula, and that formula is on the equation sheet, so you don't need to memorize it. What would be extremely helpful for you to memorize is characteristic equation of a second order system, the A matrix of the second order system, the differential equation of a second order system, so you don't have to think. You can quickly write those down, and those are going to be helpful skills no matter where you go. And so the next step asks you to find a state space model between force and displacement, and another one between force and velocity for a mass spring damper system. So the differential equation, as you know, is mx double dot plus bx dot plus kx equals force. So for both of these state space models, the x vector is made of position and velocity. The input for both is the force. Now for one of the two cases, the output is x, and for the other two case, the output is x dot. So that's the difference. I know we've done this in the past a few times, but let's do this one more time. So what you need to do for the state space, you need to find x double dot in terms of x and x dot. So if you rewrite this equation, you get x double dot equals 1 over m times minus kx minus bx dot plus f. And that is exactly what we will capture in the second row of the state space model. So x dot as the vector of x dot now is equal to 0, 1 times x. Basically, we are saying the first member of x, when it's differentiated, becomes x dot, which is equal to its second member. So 0, 1 says that. And there is no force in that equation, so 0 here. In the second row, we have minus k over m times x, so we have minus k over m. Minus b over m is multiplied by x dot, so minus b over m. And 1 over m is multiplied by the input, so 1 over m here. Now the output in one case is 1, 0 times x as a vector, and in the second case is 0, 1 times the vector. Okay, now here comes the next part. And I want to give you some time to reflect on this. It's an important question. Use the state space model to find the steady state value of position as well as steady state value of velocity to a unit step input. So you need to use the state space model to find those. So think about it, go through your notes, find the solution, and we'll discuss it together. So what is your approach for solving this problem? Let me write the general form of the state space model. So we have x dot that is equal to ax plus bu, and y is equal to cx plus du. So what are we looking for? You're looking for steady state values of the first member of the x vector as well as the second member of the x vector, knowing the input is equal to 1 and stays equal to 1 forever. That's the meaning of a unit step input. So I'm looking for your ideas on how to solve this problem. Steady state means what?
Dot terms go to 0.
Yeah, so the dot term goes to 0, which means what? Then if the dot term goes to 0 in steady state, it means ax steady state plus bu is equal to 0. That's the meaning. So from here, you know that x steady state is going to be equal to minus a inverse times b times u. And that's it. If you can find inverse of a, you simply multiply that inverse by b and multiply it by input, and you have x steady state, which includes, by the way, position steady state as the first row and velocity steady state as the second row. So let's go ahead and do this. So let's find a inverse. So it's a 2 by 2 matrix, so you move the terms, the diagonal terms. So minus b over m comes here, 0 goes here, and then the off diagonal terms will change their signs. And you take that and you divide it by the determinant. So 0 minus k over m, so it's divided by k over m. So that's the determinant of the matrix that goes as the denominator. So that's A inverse. Then you take this and multiply it by B. So let's multiply A inverse by B. So B is 2 by 1, A is 2 by 2. So the result is 2 by 1. So 2 by 2 is multiplied by 2 by 1. So we are taking row 1 and multiplying it by this. So minus B over M gets multiplied by 0. Minus 1 gets multiplied by 1 over M. So the first row is minus 1 over M. Okay, so minus 1 over M is what we get for the first row. Second row involves multiplying this second row by the column. So k over m gets multiplied by 0, 0 by 1 over m. So the result is 0. And remember, we are still dividing by k over m. That still remains. So that's A inverse times B. Then what we need to do is to we are just finding A inverse times B. We haven't plugged that back in. So x steady state, let's go here. X steady state is minus this times u. U is 1. So x steady state is essentially equal to minus this. So let's find minus of that. So this minus will cancel out. So it's 1 over m divided by k over m. So the answer is 1 over k here and 0 here. So if you give a mass spring damper system a unit step input, a force that is equal to 1 and stays equal to 1 forever, the mass is going to be displaced in, so it will go through some transition. If it is underdamped, it will oscillate. If it is critically damped, no oscillation, and as well as overdamped. But eventually it will settle at 1 over k for position, and its velocity would be 0 when it reaches steady state. And that's how we know we did something right, because if we were to find a non-zero velocity, it means we are not at steady state. The definition of a steady state is that all the dot terms have to be equal to 0. So we are reaffirming that. So let's go to number 10 and 11. So you are given now, this time, another state space model. Now, again, another point for the exam is the questions tend to be in a cluster. So there would be a few questions related to one system, again, another related to. Be aware that the questions are not just hanging there without any system. So don't make the wrong assumptions. I'll try to make it as clear as possible that this question is related to what system, but please be aware that the questions come in clusters, like this one. So you have a system expressed in this state space model. A and B and C are given. D is not given, but it means D is 0. Show that this system is observable. So because observability is the last thing we covered, I want you to do this first, and then I'll show you the solution. So see if this system is observable first. And then if it is observable, it means you can design an observer. Design an observer with repeated poles. This is a typo. These are not repeated. Drop the repeated. So poles at negative 13, negative 3 and negative 12. So when it says repeated, they should be at the same place, but they're not. So that's simply design an observer with 2 poles, one at negative 3, the other one at negative 12. So let's start with the observability matrix. This is a second order system. The observability matrix will have the same dimension as matrix A. So it means it's 2 by 2. So the highest power of A that it will include is power 1. This is order 2. second order system. So C is the first row of the observability matrix. C times A, which would be another row matrix, would be the second row of that. So what we need to do is to calculate C times A. So C is 0, 1. So column 1 becomes 1, column 2 becomes -2. So assemble the observability matrix. C, which is 0, 1, goes row 1. CA, which is 1 minus 2, goes row 2. And then we calculate the determinant. The determinant is -1, which is non-zero, so that means the system is observable. Did you get the same thing? If not, let me know and I'll correct my calculation. Or if something is not quite clear, let me know and I'll explain before moving to the next step. Yes?
Can you explain CA again?
Yeah, CA is C times A. So C is 0, 1. C is 0, 1. So this is 1 by 2, 1 row, 2 columns, which is now multiplied by 2 by 2. So the result is 1 by 2. So this row gets multiplied by the first column. So 0 multiplied by -1, 1 multiplied by 1. They get added up. The first column is 1. And similarly, 0 for the second column gets multiplied by 0. 1 gets multiplied by -2, and they get added up. So 1, -2. Okay, so let's move forward and design our observer. So designing observer means recognizing that A of the observer is A minus L times C. So let's go ahead and again calculate L times C. C is 1 by 2, so L is 2 by 1. So L1, L2 times C was 0, 1. So 0, 1. So this is 2 by 2. L1 times 0 is 0. L1 times 1 is L1. 0, L2. This is L times C2. We need to subtract this from L, so from A rather. A is right here. So that means 0 gets subtracted from -1, so it's -1. L gets subtracted from 0, so minus L1. 0 from 1, so it's 1. L1 from -2, so -2 minus L2 rather. So this is A of the observer. So how can we make sure that the eigenvalues are at -3 and -12? We need to just calculate the eigenvalues. So we will set up lambda I minus A of the observer, which will give us lambda plus 1, L1 minus 1, lambda plus 2 plus L2. So you calculate this coefficient, you find the polynomial, and you make sure that this polynomial is equal to lambda plus 3 times lambda plus 12 by equating the coefficients of lambda to power 1 and lambda to power 0. Once you equate that, you will get L1 and L2, which is the design, end of the design of the observer. So I'll let you finish that. And question number 12, I believe this is the last question. Find, for a standard second order system, find the closed loop transfer function with a proportional controller. This means output feedback. Output feedback. Also find the root locus for the closed loop system and explain the effect of controller gain on the step response of the closed loop system. So that's what we are trying to solve. So for a standard second order system, the transfer function g of s is 1 over ms squared plus b times s plus k. That's the transfer function. Now, a proportional controller means you have g of s, you feed back the output and only the output, and you send it to this proportional gain, which then defines the input of the system. That's a proportional controller, otherwise known as output feedback. So we need to find the closed loop transfer function, which means we are trying to find y over r, and that is going to be equal to kp times g of s in the numerator, 1 plus kp times g of s in the denominator. This would be the closed loop transfer function once you plug in g of s and simplify by making the denominator the common denominator. So that's the closed loop transfer function. And if you're trying to find the root locus, essentially you're trying to find what values of s will make the denominator go to 0. So s1 and 2 would be minus b plus minus square root of b squared minus 4 times k plus kp times m divided by 2m. Now it all depends on where the open loop eigenvalues are located. If this system is overdamped, in open loop it will have 2 real and negative eigenvalues. If it is critically damped system, it will have 2 repeated real and negative eigenvalues. If it is underdamped, the open loop system would have a pair of complex conjugates. So you need to make one of these assumptions and make it absolutely clear what are you assuming. What are you assuming for the open loop to be the case? So essentially, you're making an assumption that will tell you what is happening here under the square root. Is this a real number? Is this a positive number? If it is a number that is equal to 0 at open loop, or it's a negative number, you need to make that absolutely clear so the starting point is clear. So let's look at an interesting case. So let's assume that at the beginning you have 2 identically located open loop eigenvalues, which means when kp is 0, under the square root is exactly equal to 0. Let's make that assumption. So assumption, open loop is critically damped, which means 2 real and negative eigenvalues. So that's in open loop. So now you need to answer this question. As kp increases from 0 to larger numbers, what happens to those 2 eigenvalues? Where do they go on the complex plane? Where? You have the expression right here. Would B change at all as you change kp? By the way, B is the value of the real part. Under the square root is 0, So what you have is minus b over 2m. That's the value of the two real poles. Now as kp increases, the fact that b squared minus 4 times k times m is 0 is still the fact. That is still 0. So as k increases, you start having a negative value under the square root, which gets larger and larger and larger without affecting the real part. So what is the shape of the root locus? The root locus basically looks like this. It's going to go up from here and down from here. So as kp goes up, that is the shape of the root locus. So the two real parts, the real part remains the same, just the imaginary part gets larger and larger and larger. So that tells you in the final exam, if you have a question similar to that is not clear, it's not clear where the open loop eigenvalues are located, you can simply put 2 in without any explanation. So you need to make any assumption that you make very clear. Otherwise, how could I know that you're just guessing or it is based on any calculation? So you don't want to leave anything out for me to guess, because you're not going to get the grade that you deserve. So if you make an assumption, make it super clear. That is the assumption I'm making, and therefore this is what is happening. Any questions on this exam? And the same shape would exist if you had a pair of complex conjugate, by the way. So if the under square root was already negative when kp was 0, the only thing that would happen is that negative would become larger in value. So it would be two poles that would, again, get farther separated from the real axis. If you had two poles that were negative and real and non-repeated, what would happen is as kp increases, they would come closer to each other, they will meet, and then we'll have the shape that we have here. So there are three possibilities here. Okay, I'll stop here.